Let's take a look at the factorization of this quintic polynomial, fifth degree. 3x to the fifth minus 5x to the fourth minus 8x cubed plus 16x squared plus 21x plus 5. There actually is no formula that generally factors every single quintic polynomial, and so we must resort to the techniques taught in pre-calculus. So first thing we'll do is identify the possible rational roots in the hopes that at least one of these might work. So the numerator will be things that go into the constant term, plus or minus 1 or plus or minus 5. And the denominator will be things that go into the leading coefficient, plus or minus 1 and plus or minus 3. So factors of 5 on the numerator, factors of 3 in the denominator. And so this gives us a list of 8 candidates, plus or minus 1, plus or minus 5, plus or minus a third, and plus or minus 5/3. Obviously, not all 8 of these will work. It's a fifth degree polynomial, so not all 8 will work. And there's no promise that any of them will work. Now, to get started, let's take a look at the graph. And we see that it looks like we have an x-intercept at -1. And furthermore, the graph of the function touches the x-axis. So it comes up and then touches and comes down. So that's a guess that -1 might be a multiple root. Looks like there's also another root over here, somewhere between 0 and -0.5. And those are the two x-intercepts. So based on the graph, let's try -1 first. So 3, -5, -8, 16, 21, 5. And if I plug in, so 3 comes down, 3 times -1 is -3. -5 plus -3 is -8. -8 times -1 is 0. 8. -8 plus 8 is 0. Got ahead of myself. 0 times -1 is 0. 16 plus 0 is 16. 16 times -1 is -16. 21 plus -16 is 5. 5 times -1 is -5, and I get 0 as my remainder. So this shows that it does indeed factor. Okay, now it turns out that it works again. One way to check that -1 is a root is to actually plug in -1. If I were to plug -1 into this, I would get 0. However, by plugging in -1, that would not tell me that it's a double root. To check it's a double root, I apply synthetic division again. And I apply synthetic division to the quotient that I have here. 3 times -1 is -3. -8 plus -3 is -11. -11 times -1 is 11. 0 plus 11 is 11. 11 times -1 is -11. 6 plus -11 is 5. 5 times -1 is -5, and 0. And so that shows that -1 is a double root. Okay, now I'm down to a cubic. Taking a look back at the picture, I have another intercept here between 0 and -0.5. So that makes me hopeful that -1/3 is the other one. So looking at my possible roots, the only other rational root that might work is -1/3. Now the graph does not prove that it works, but it makes me think that it works. So let's try -1/3. 3 times -1/3 is -1. -11 plus -1 is -12. -12 times -1/3 is +4. 11 plus 4 is 15. 15 times -1/3 is -5, and I get 0 as my remainder again. Please note that to check -1/3 was a root, I did not go back to the original quintic. I used the factorization that I had to make it even simpler. So I've shown that f of x is equal to x plus 1 squared. Then I've got x plus a third, and then 3x squared minus 12x plus 15. Okay, and so I can factor 3 out of the last bit. So 3 times x plus 1 squared times x plus a third, then x squared minus 4x plus 5. Okay, so to figure out the roots of the quadratic part, I'll use the quadratic formula. X is equal to -b plus or minus square root of b squared minus 4ac over 2. So this is 4 plus or minus 2i over 2 for for 2 plus or minus I. So this does not factor any further over the real numbers, and the roots of this quintic polynomial are -1 with multiplicity 2, -1/3, and 2 plus or minus I. So 2, 3, 4, 5 roots, as we would expect for this 5th degree polynomial.